So here in part 2, we're going to show you how you can use PCA in Unscrambler to analyze our sensory data. And PCA, of course, is principal component analysis. If you're not familiar with the concept of it, I'll just briefly introduce you to it. PCA is known as a dimension reduction technique, in that it attempts to reduce the data down to a lower number of dimensions whilst trying to retain, hopefully, a large proportion of the explainable variance. And at the heart of this technique is the idea that if two or more variables correlate strongly with one another, then they're probably measuring the same underlying component. PCA works by identifying these correlations between groups of variables with the aim of, if you like, distilling these underlying components that account for their variation. And the procedure can then turn these selected components into data, into new variables that show where each individual data record or data point lies on each respective component scale. So examples of PCA would include analysis that attempts to uncover, if you like, the themes in a data set. For example, what nutritional elements tend to co-occur in different foodstuffs. Or in the same vein, PCA could be used in material sciences applications to try and reduce the dimensions of a data set measuring the spectra of different alloys. And moreover, traditionally analysts have used PCA to reduce the number of variables used in building a predictive model by entering only the principal components that explain the most variation. So if you're dealing with a very wide data set, it means you don't have to put in all of the variables. You can do a principal components analysis and enter only those components that explain the most variation and hopefully still get an accurate prediction out the back of it. So the way to think of it is each variable is a kind of cocktail of variation. They are distinct from one another, yet they share common ingredients, in the same sense that you could look at a set of cocktails and say, well, these ones have a high alcohol content, these ones here have a lot of citrus in them, and these ones over here have a lot of sugar in them, and you could kind of separate them out. Therefore, if two cocktails are similar, it's because they share the same components or characteristics. So PCA is very much about distilling those underlying components and almost unmixing the cocktails. It produces a solution showing which variables strongly correlate with each component, and in many ways the job of the analyst is to try and interpret the strongest components in a meaningful way. But it also shows in descending order how much variation each factor or each component can explain. So imagine if you have a data set with 10 variables and you want to reduce the data down to uncover the principal components that explain the variation in the file. The principal components analysis will run and it will produce 10 principal components. And those 10 principal components, representing different combinations of the original 10 variables, will explain 100% of the variation. But that rather defeats the point of it, where you're trying to actually reduce the dimensionality. If you look further, you may notice, for example, that 60% of the variation can be explained using only the top 2 principal components, and that if you go to 3 principal components, you can actually explain 75% of the variation. In the same sense, we can plot this as if these were new variables that we've created, principal component 1 against principal component 2, and show where the data points relate to one another in these various axes. Here, for example, principal component 1, PC1 here, explains 66% of the variation in the data. It's actually picking up the protein content in these different foodstuffs from a fast food outlet. Whereas principal component 2 explains 24% of the remaining data. That's really picking up, it's strongly related to the fat content of these different foodstuffs. So right away, by using principal components analysis, we're able to explain 90% of the variation from simply 2 components. So we've reduced, if you like, the 10 variables down to 2 primary components. Let's have a look at how that works with our sensory example in Unscrambler. Okay, so we've opened up Unscrambler, and as you can see here, we're working with version 11 of the software. If I just quickly show you the file menu, if we were importing data and starting from scratch, we'd go down to File, Import Data, and it's just interesting to point out that there's a very wide range of different file types. Many of them are, vast majority of them are proprietary file types that we can import. In this case, we're actually going to open up a little project file which is going to contain our data as well. This project file is, as I said, part of the tutorial in Unscrambler. So if I go to open here, you can see it's under the data folder in Unscrambler, and we're looking for tutorial B, which relates to our example with checking the quality of raspberry jam samples. You can see that there are 20 samples in total, 12 of which we have complete information for. That's effectively our training data, and then our test data, if you think our prediction data, contains only data related to sensory, the sensory evaluations. If we expand the project folder out here, you can see that actually there's some metadata that's been defined here. Again, training here simply selects the training data. Prediction is our test or prediction data, which is our last 8 rows. In the same sense, in the columns here we can isolate the instrumental variables, the single preference variable, which is the consumer liking variable, and the sensory data. And what we're going to do is we're going to create a couple of categorical variables which relate to the agronomic information, which is the cultivar and the harvest time that was used. So to do that, if I just go back to the raw data here and highlight, say, the first column, and then go to Edit, and we'll go to Insert. So we're going to insert a categorical field, a categorical variable, and we'll call this one harvest time. And we just need to define it manually here, which I'll call H1 to H3. We do the same thing with our field cultivar. So we're going to create a categorical variable called cultivar. We go to File, Insert, Category Field. Let me call this one cultivar. And we call this C1, of course, through the C4. So what we've done is we've basically created the shell for these data. We now need to populate the information here. So if I go to cultivar here, I could just highlight say the first, for cultivar 1 here, just the first 3 rows, and then right click and go to fill, and fill in cultivar 1, and do the same thing for cultivar 2 and 3 and 4. And then for harvest time, we'll pick them individually. So you can see that these row sets have already been defined here, and these column sets have been defined. These are we can view these, if you like, and confirm that they've been defined correctly by going to Edit Define Range, and there they are. There's the column ranges. There's the row ranges been created. We're actually going to create our own group rows. So we're basically going to create a new set of row sets here that relate to the cultivar type. So we're going to go to Edit, and this is just generally good practice. It's just part of the tutorial, and it's good practice and helps us with selecting the relevant data for the analysis later on, and it also helps with labeling the data appropriately when we're doing the analysis and creating plots. So I go down here to Edit Group Rows. I can just select this, actually select this first column here, and go to Edit Group Rows, and just click OK automatically, and it just creates, as you can see, a row set for C1, C2, C3, and C4. And having defined the data and set it up correctly, we were now ready to do a principal components analysis. So to run the PCA, we're just going to go up to Tasks here and click on Analyze, and about a third of the way down we've got Principal Component Analysis. We click on that, and then we're going to go down through a wizard and make a number of selections. So the first thing we want to do is select the range of data we want. So what rows of data do we want to include? Well, we want to include the training rows, which are 12 rows of data where we have some sensory information for all of these guys. And we're going to go to choose from the columns, a subset of the columns. We're going to choose the sensory columns, of which there are 12. I'm going to reduce the number of components down to 6 and ask it to identify outliers as well, because that's useful information to have. If I hit next at this point, it does give you the option to weight the data, and by weighting here, it could take the form of effectively standardizing the data, taming it and putting it into the same units. It can be useful when you're dealing with very inconsistent information where you've got different people making, you know, very different assessments, if you like. You must remember, of course, that these are averages of the scores there, and it's based on a pretty professional and experienced panel, which means that we can pretty much assume that they're fairly consistent and reliable in their assessments, in their sensory assessments. So we're not going to weight the data in this case. We don't need to do so. We hit next at that point. Then we get the validation. It does rather assume you're going to validate the data here, and the default validation is full default, the full validation method. Validation, of course, is where we build the model and all the data, and then we apply the model back, having built it on all but one of the cases in turn. So it's repeatedly building the model again 12 times. So it can be quite a resource intensive process. And the result is that it gives us an idea of how stable the model is, how likely we are to get the same results on a comparable sample, and gives us some sort of reassurance here. So validation, we're going to go with full validation, then go to next. And I'm just going to choose finally here the NIPALS algorithm because it's a simpler algorithm. It's easier particularly for beginners to interpret. If we hit finish at that point, what we notice is that we see some plots that have been generated, but in reality this is only part of the output that we're being shown here in the PCA part of the project tree. We actually have the raw data. We have lots of different results in numerical format which we can look at if we so wish. We have information about validation and convergence, and then we get down to what we've been shown here is the overview plot. That's the first one we've been shown. There's actually lots of other plots that you can zoom into. There's a vast amount of information we can get out of this analysis. In fact, we're just going to focus on the principal components overview plots here because there's actually quite a lot we can do. And we're going to look at the 4 different charts in order. We're looking at the scores chart here. So the scores chart here is referring to the individual rows of data, if you like, the different samples. And one of the things we can do, for example, is just obviously switch on things like our labels. So we can see here that we have cultivar 1 and harvest 1 and cultivar 2, harvest 2. And we can also see, very importantly, that we're looking at a plot here of principal component 1 against principal component 2. Principal component 1 just on its own explains 58% of the variance in the data, and principal component 2 explains 28% of the variance in the data. So, you know, it's quite a lot of information that's being soaked up, a lot of variation that's being accounted for just using 2 components. We've got 86% explained using just 2 components. If we wanted to change this, just so you're out of interest, we could switch this to one of these axes to PC3. We can see that principal component 3 explains 11% of the data. So right away we're well north of 90% of the data being explained by simply 3 of our components. And we can also see this explained variance here shown in this chart at the bottom here with a validation line. So the validation here, of course, is represented as red, and calibration, our main sample data, if a model building sample, if you like, is the blue line. And we normally would expect the validation to be slightly less than the calibration line, but they're pretty closely matched. And we can see here that, you know, we reach 90% by the time we get to principal component 3. Adding in principal component 4 and 5 and 6, they probably don't explain that much of the variation. If we just looked at principal component 4 here and saw how much variation, it's 1%. It's barely worth retaining. So in terms of our goal to reduce down the data, reduce the dimensionality of the data, and explain the majority of the variation with a fewer number of dimensions, we definitely hit that goal because we're explaining the vast majority of the data with 2 or 3 different principal components. So these are the cases themselves that we're looking at here. If we look over here, we have information which is basically in the form of our actual variable loadings. This is our variable loadings here, and you can see that these are saying where these fields tend to load on the different principal components. So for example, if I'm looking at PC1 here, I can see that as a dimension, it seems to be related to the color and the thickness. Okay, so it seems to be thickness, redness, and color, and I suppose that makes sense because if the sample isn't very thick, it might be a paler color. That makes sense. If it's less viscous, it might be a paler color, and if it's thicker, it might be redder. We can also ask it to center this. So if I use a correlations loading measure here, this is quite a good way. You suddenly find that standardizes it now around 0 and 0. And this is useful because it's telling us which fields are loading particularly high on these two different components. The inner circle, the inner ellipse here, refers to the middle 50% of the explained variance, and the outer circle here means that if any fields mentioned in these outer circle means that they are explaining more than 50% of the variance. So they're loading higher than that, if you like. They're particularly strongly related to that. So you can see redness and thickness are on this dimension here related to color, if you like. And then we have flavor, which seems to be related to things like smell and flavor, and off flavors as well, which is off flavor up there. So there's definitely something going on with flavor there. We could also play around with this and say, well, let's look at principal component 3, put that in there. You can see that seems to be related to bitterness and chewiness and sweetness. So these are the dimensions. These are we really need to perhaps spend a wee bit more time digging into that and figuring out what's happening there. But clearly the color and or thickness really helps us discriminate between these different samples here. And while we're looking at these different samples, if I right click over here and go to sample grouping, you'll see that currently it's just showing us the case labels, if you like. But I could actually ask it to switch down to the category variables and say, okay, show me this by cultivar, and hit apply. So now we can just see the different cultivars, C1, C2, C3. You can see that the C4 ones are kind of similar here. The other ones are kind of grouped around in different bits. So it doesn't seem to me to be that clear which ones, how they're separating, how the different dimensions are separating out the cultivars. Though it's true to say that cultivar 1 does tend to load higher, as we can see in this top part up here on principal component 2, and cultivar 3, well, 2 out of 3 of them are loading higher on principal component 1. But I actually find it clearer if I go down here and ask it to show me it by harvest time. And if I say, okay, show by harvest time and color by harvest time, it's very interesting because we can see here we're getting good separation, good clustering here of harvest 1 versus harvest 2. And then harvest 3 is kind of this linear, this diagonal grouping here of these three different groups, which indicates to me that you could use these two principal components alone in a classification model, and it would probably do a reasonably good job, if not a very good job, of predicting which harvest the different samples came from, which is very interesting. Okay, if we look down here, we hit cancel. Let's go down to the influence here, and we'll just switch on our labels here. So just so that you're aware what intervals, Hotelling's t-square is a measure really of how close to the center of the model the data point is, or how well it fits the model, whereas the residual value here is really how much information is left over, how much unexplained information is left. And if you're getting cases here or individual observations which are very high on Hotelling's t-square and very high on the residuals, then it does indicate that they're somewhat extreme. In this case, they're not particularly extreme. These two red lines really relate to the 95% confidence intervals, if you like. So, and they're not crossing that. It's basically indicating that they're all fairly similar. So just a few things to finish up here. So explained variance can be shown as a line chart. You can notice when you click on this chart here, you can also ask it to show it as a bar chart. And here we have the red for the validation and blue for our calibration. In the same sense, if I go up here and I say, okay, don't show me the explained, but show me the residual, that's the unexplained. And of course, as we add more dimensions in, we've got less unexplained variance, so they're less residual. In the same sense over here, we can ask it to show the calibration and the validation samples. So we can see that they're generally quite closely related to one another, though Harvest 1 for validation and calibration are somewhat different. Again, we can show the labels here. And the same thing over here, where we can ask it to go a little bit deeper and show us, you know, the relationship, say, between PC1 and PC3, and play around with these extra values. So what have we learned from doing this? Well, we've learned a number of things. We've learned, first of all, that with 3 dimensions, or 3 components, if you like, we can actually explain the vast majority of the variation in the sensory testing. We've also discovered that there's a reasonably good fit between the validation and the calibration samples, so it seems to be a fairly stable model. We know that from the influence plot that there aren't any real troublesome extreme samples in there, and we can get a sense of what the principal components themselves are measuring by looking at the correlation loading plots, which is this relationship between redness and thickness, or the color, if you like, of the samples, and also with regard to the flavor and smell and off flavors. And the third component here, if we look at the third component here, we've got bitterness and sweetness as our third dimension. So we've learned quite a lot. In the next example, we're going to take this a little bit further, and we're going to look at partial least squares, and we're going to combine in our data related to the instrument measurements that we haven't included thus far in an analysis.